All right, sorry about that, but the program that I'm using to make these screencasts, because it's a free version, will only allow me to record 15 minutes at a time, so it kicked me out. So just continuing on then, if I look at a Maxwell-Boltzmann distribution curve, for most organic reactions, biological based reactions, the activation energies are quite high. And because of that, a very modest change in temperature will shift the curve subtly, but sufficiently, so that there is a significantly larger fraction of particles that has that activation energy. So you don't need to double the kinetic energy in order to double the rate. All you need to do is double that fraction of molecules. So to answer the question, how then can a subtle change in temperature double the rate of reaction? Well, all that needs to happen in order to double the reaction rate, all that needs to happen is that the fraction, the total fraction of particles with activation energy or higher, needs to double. The total fraction of molecules with that minimum kinetic energy, that activation energy, must double. And for that to happen, you don't need to shift the curve a lot, especially if the activation energy is quite high. If the activation energy were lower, then small changes in temperature don't have as large an effect. All right, 2 more questions. What is the effect on the number of molecules possessing activation energy at some new lower temperature? What is the effect on the value of EA at that new temperature? So when we talk about the number of molecules, we're looking at that, again, that total fraction, the area of the curve that is past that activation energy. This question is very similar to the one we just did. Basically, it's just forcing us to draw the curve one more time. It's important to be comfortable drawing these curves. So again, kinetic energy, again, fraction of molecules. So I'll have my original reaction, something like this. We'll place our activation energy, EA, and at some lower temperature, remember, it still anchors at 0, 0. The curve will be taller. The area has to be the same. And we see that the total fraction of molecules, the total number of molecules with activation energy or higher, with that minimum kinetic energy for effective collisions, that area of the curve is much smaller than it was before. And because of that, the rate of the reaction should decrease. So to answer the question, the number of molecules, that is the total fraction of molecules with activation energy higher, is now lower than before, and therefore the rate of reaction is slower. Rate of reaction is slower at the new lower temperature. So this is why changing temperature affects reaction rate. This is why at higher temperatures rates increase. This is why at lower temperatures rates decrease. Now, at a higher temperature, particles move faster, and so therefore there are more collisions at faster speeds than at lower speeds. But more significant than the number of collisions going up is the fraction of molecules that has this activation energy, because of the way that the distribution of molecules changes as the temperature changes. Final question then, we've got two reactions, R1, R2. They're at the same temperature, but the activation energy of reaction 1 of R1, so we'll call that EA1, is greater than EA2. Decide which reaction is faster and explain why. So I'd like for you to draw a Maxwell-Boltzmann distribution curve for both reactions 1 and 2. Label the EAs of reactions 1 and 2, and answer the question. And that will be it for today. And when I see you next day, we'll do some demos looking at factors affecting rates of reaction.